Okay, let's unpack this. We have a massive, highly strategic document in front of us detailing the future of intelligent connected infrastructure, laying out a plan that stretches all the way to 2040.
It's quite something, isn't it?
It is. And this isn't just, a white paper full of optimistic forecasts. This is essentially a strategic technological status report and a brutally honest development roadmap.
That's right. It's framed around a multi-decade mission to build a hyper-efficient, self-evolving transportation ecosystem, basically from the ground up.
And when you look at this through that lens of strategic consultancy, analyzing the tech status and the future direction, what we have is the blueprint for a fundamental system overhaul.
It's often called the Intelligent Connected Infrastructure Technology Roadmap. And our mission in this deep dive is to really extract the quantifiable goals, the strategic milestones, and I think the core philosophies that are going to guide the next 2 decades.
Specifically focusing on those three main pillars, right?
Exactly. We're talking automatic driving maps, high-precision positioning, and smart road infrastructure. This whole endeavor is designed to transition transportation from its current state of isolated systems.
Where every car is basically fighting for itself on the road.
Yes, precisely. From that into a single, cohesive, tightly collaborative, closed-loop ecosystem.
That immediately establishes the stakes. It's not about making individual cars slightly better, it's about connecting the entire national nervous system. So what exactly is the 2040 vision for this closed loop? What is the finished product, the ultimate end state we're driving toward?
The ultimate goal is the construction of a symbiotic, highly efficient network that functions almost like a self-optimizing organism.
An organism, I like that analogy.
It's formed by three primary interacting components. You have the intelligent connected vehicles, the foundational time-space data platform, and then the smart cities and their infrastructure.
And this fusion isn't just about getting from A to B faster.
No, not at all. The strategic justification is the holistic economic benefit, aiming for maximized energy efficiency, maximized traffic flow, which, means less time for all of us sitting in jams, and critically, minimizing the overall social operating costs across the entire network.
So the system has to be continuously learning and optimizing. That's the self-evolving part.
That's the key. It never stops improving.
Okay, so that kind of closed-loop ecosystem needs incredibly strong structural support. If the ecosystem is the closed loop, what are the four strategic pillars that provide the essential structural support for this 2040 vision?
They are the functional components that make the whole thing work, that enable that self-evolution. First, you have the intelligent connected vehicles.
Cars themselves.
The cars, the trucks, the buses. They're the mobile clients, acting as the service carriers, and, crucially, the dynamic data source that feeds the loop. They're the eyes and ears on the ground.
Okay, so that's pillar one. What's number two?
Second is the automatic driving maps. This is the time-space data platform itself. It provides the crucial cognitive foundation, you could call it the necessary prior knowledge, and enables continuous, high-fidelity data updates for the entire system.
And pillar three must be knowing where you are on that map with incredible precision.
You've got it. Third is high-precision positioning. This is the essential global guarantee. It offers real-time, centimeter-level, highly reliable location service across the entire network. It ensures every vehicle knows exactly where it is in the context of that map.
Centimeter level, that's astounding. And the final pillar.
And finally, smart road infrastructure. This acts as the vehicle's extended perception system. It gathers data beyond the vehicle's line of sight, ensuring safety redundancy and enabling that coordinated network-wide control we talked about.
Okay, let's unpack this. Before we dive deep into the technical roadmaps for each of those pillars, the analysis identifies this major strategic pivot, the reason why this expensive, massive overhaul is necessary right now. It's driven by two core, often complementary concepts. What are those foundational philosophies driving this whole paradigm shift?
This is where we move from, incremental improvement to a fundamental redesign. The strategic calculus acknowledges that the current path relying solely on complex L3 single-vehicle systems is proving to be too fragile and, frankly, too expensive to scale rapidly.
Too fragile and too expensive. That's the central conflict this roadmap is designed to solve.
Exactly. The first strategic shift relates to single-vehicle intelligence evolution, and it's encapsulated by this really telling concept. Light map plus heavy perception.
Light map, heavy perception. That phrase itself hints at a big economic trade-off. It sounds like automakers are trying to move away from relying on these costly, high-maintenance data structures.
You've nailed the economic calculus for the automakers. They have to find the optimal balance between the prohibitive cost of maintaining complex, high-definition or HD map databases and the continually dropping cost and improving capability of onboard sensor systems.
That's the heavy perception side of the equation.
That's it. Traditionally, HD maps were incredibly complex. They required specialized collection vehicles, they were slow to update because of regulatory hurdles, and therefore they were just very, very expensive to deploy across a large geographic footprint.
So the strategic shift is to reduce the vehicle's reliance on those massive static HD maps.
Precisely. The map doesn't disappear, but its role changes dramatically. It moves from being the primary source of truth to becoming more of a foundational skeleton.
A skeleton. Okay, so what does that mean in practice?
It means the map becomes a lightweight data structure. It's a foundation that provides basic, stable topology like the fundamental road and lane geometry. This basic map is then instantly and continuously supplemented by the vehicle's sophisticated real-time sensing suite, the cameras, LiDAR, and radar.
And the impact of that shift is what? Lower costs.
Revolutionary. It significantly lowers the cost of entry and reduces the development difficulty associated with autonomous driving. And that, in turn, accelerates deployment into a much broader range of city and suburban scenarios, which were previously just too costly to map and maintain at that full HD quality.
That makes perfect sense for lowering costs and accelerating L3 deployment. But as you said, the single vehicle intelligence model hits a ceiling. It can't see around corners through a traffic jam or in heavy fog.
It can't.
And that brings us to the second core concept, which is absolutely vital for moving to true L4, L5 autonomy, the overarching system architecture upgrade.
This second concept is the strategic anchor for the whole plan: vehicle road cloud integration. This is the mandatory move to overcome the inherent physical limitations of single vehicle intelligence.
The line of sight problem.
Exactly, the line of sight problem. A car's sensors are restricted by what they can physically see. A sudden lane blockage, a child running from behind a parked bus, or a severe localized weather event. These are all threats that a single car may perceive too late to react safely.
So, if the car can't see far enough or through the obstruction, the road infrastructure is designed to provide that crucial extra layer of visibility.
That's exactly right. The road infrastructure is deliberately treated as the extended perception system. Roadside units equipped with high-resolution cameras, smart radars, and edge computing gather data far beyond the vehicle's range or line of sight.
And then what happens to that data?
This external data is then fused with the vehicle's internal data, and collaborative decision-making occurs instantaneously via the cloud control platform. This comprehensive three-way architecture vehicle, road, and cloud is absolutely crucial for realizing the safety and redundancy required for Level 4 and Level 5 autonomy.
So it moves the system from inefficient single-unit combat
To sophisticated, optimized network-wide coordination. It's a total game changer.
So vehicle road cloud integration is the only structural way to break that safety and efficiency ceiling for high-level autonomy. Okay. Before we move on to the aggressive 2040 roadmaps, the analysis includes a quick check-in on the status of the previous strategy, RoadMap 2.0, which covered goals up to 2025.
A reality check, yeah.
How did the industry fare against those earlier goals?
The assessment shows a really interesting pattern. We see a pattern of achieving technical accuracy early, but then struggling with regulatory scalability and cost control, the very problems the 2040 roadmap is now designed to fix.
Okay, let's start with the maps.
For map status, by the 2024 checkpoint, the accuracy goals achieving sub-meter and decimeter levels and the application in key scenarios like HA-level driving were achieved. That's a technical success, no doubt. But the critical goals for rapid update frequency and the construction of the foundational service platform still lag behind.
And what was the primary cause of that lag, given that the technology was clearly ready?
Primarily two things: regulatory friction at high compliance costs. The regulatory landscape, which rightly prioritizes national security and geographic data safety, complicated the quick, crowdsourced data updates that the technology was enabling.
It created a gap.
A massive gap between what the vehicles could sense and report in real time and what regulations allowed them to incorporate into the official HD map database quickly and legally. This policy bottleneck just slowed down the whole self-evolving aspect of the system.
What about positioning status? That seems like a slightly more mature, maybe less contentious technical field.
Positioning status actually achieved its targets ahead of schedule, which is excellent news. Centimeter-level positioning accuracy was largely met by the end of 2023, beating the 2025 target.
So what's the catch there?
The catch, just like with maps, remains in the industrialization phase. We're talking about mass production maturity, stringent cost control, securing the supply chain completeness, and achieving autonomy in core hardware.
So we have the accuracy.
We have the accuracy, but we still need the scale and the domestic independence in high-end components like navigation chips and specialized inertial components.
That sets the stage perfectly. We achieved the accuracy targets for maps and positioning early, but scalability, cost, regulatory bottlenecks, and foreign hardware reliance are forcing this new, hyper-aggressive, and highly coordinated 2040 strategy.
So it's a whole story right there.
Let's start the deep dive into Pillar 1 then, automatic driving maps. This is the spatial knowledge base of the entire ecosystem.
To truly understand the 2040 vision for maps, we have to first recognize that they are not just pictures or lines on a screen. They are a sophisticated, multi-layered data model that provides crucial spatial knowledge and cognitive support. It's the ultimate prior knowledge to the autonomous vehicle.
If we're achieving centimeter-level driving, the map has to provide centimeter-level knowledge.
It has to. They're two sides of the same coin.
Let's break down the spatial knowledge base. The source material details 7 key layers. How are these layers structured, and how do they scale up from basic navigation to full L5 autonomy?
We can categorize the map into 3 main tiers, and they're defined by the level of detail, the accuracy, and of course the update frequency required.
Okay, Tier 1.
The first tier is the basic standard navigation maps, L1, L3. This uses the 2 most superficial layers, the road network layer and the macroscopic traffic information layer. This is the standard GPS map we all use daily on our phones.
So 5 to 10 meter accuracy, updated maybe quarterly or yearly.
Exactly. It gives you basic path planning and general directions. It'll get you to the right street.
That's useful for me, but completely useless for a self-driving car at highway speed. So the next tier must introduce the necessary precision for assisted functions.
That's the leap to the advanced driver assistance maps, L1, L4. This adds the road lane connection layer and the crucial lane level road network layer. Now the accuracy tightens considerably. We're in the sub-meter range, say 0.5 to 1 meter. And what does that extra detail enable? This map provides critical lane level guidance, detailed curvature profiles, and connectivity relations. This is essential for functions like navigation on autopilot, or NOA. And these require much fresher data, updated monthly or quarterly at a minimum.
And finally, the ultimate goal. The true high-precision maps, HD maps, required for unsupervised L4 and L5 driving, the cognitive level.
This third tier incorporates all 7 layers. It adds the map feature information layer, which includes detailed static objects like traffic lights and signs. Then there's the dynamic perception container layer, which handles real-time data like temporary construction zones or recent accidents.
And the most important one?
And the critical intelligent decision support layer. This is the full knowledge base where accuracy has to be stringent, aiming for 0.2 meters, 20 centimeters, or even better. These HD maps require updates that are almost continuous, daily, weekly, or monthly, depending on how dynamic the area is.
Let's spend a moment on that 7th layer, the intelligent decision support layer. It seems to be the cognitive difference between just a standard map and a true knowledge base. What does it actually do for the vehicle?
It shifts the map from being a geometric database to being a set of driving instructions. Layer 7 is where the map tells the car, not just what is there, but what to do.
Can you give me an example?
Sure. It pre-calculates optimal speed profiles for curves or complex merge points. It can identify the precise location for high-speed platooning to save fuel, or it can even provide crucial fallback strategies in the event of a sensor failure.
So it's a repository for complex, localized rules and derived knowledge.
That's it. It allows the autonomous system to think several steps ahead and really to guarantee safety.
That explains why this HD map foundation is deemed necessary for L4, L5, even with the heavy perception trend. It's the ultimate safety net. It provides the crucial context the sensors might momentarily lose, ensuring regulatory compliance and reliability.
It provides the redundancy. Think about it. If you are driving unsupervised on a highway in heavy rain and your LiDAR is degraded, the HD map, combined with centimeter-level positioning, ensures the vehicle still knows the exact curvature of the road, the lane boundaries, and the location of fixed infrastructure.
Preventing catastrophic failure.
That's what it's all about.
Now let's pivot to the future trends. How is the process of creating and maintaining this complex, seven-layered knowledge base going to evolve to meet those 2040 coverage and update frequency goals?
The analysis highlights 4 critical future trends, and they're all heavily accelerated by artificial intelligence and connectivity. The first is a profound AI-driven revolution in mapping.
Which ideally gets rid of those expensive manual mapping vehicles we mentioned earlier.
Exactly. AI large models are transitioning maps from being simple perception models, which required intense human validation to translate sensor data into map features, to becoming cognitive and generative models.
What does that mean, generative models?
It means AI can now efficiently analyze massive volumes of crowdsourced data from millions of vehicles, automatically recognizing and extracting terrain, road features, and signs. This shift radically accelerates map production, reduces the need for costly manpower, and ensures data freshness. The collection process becomes a continuous background activity of the entire vehicle fleet.
This links directly to the second trend, moving from a geometric database, just lines, and points to a semantic knowledge base.
The map's utility now lies in its meaning, not just its measurements. Semantic enhancement means deeply integrating logical information. Think about translating a painted line on the road into a specific legal rule,
Like identifying a school zone or defining a dedicated truck lane.
or marking a temporary construction area. This also involves dynamic scene fusion, using technologies like VSLAM or real-time LiDAR data to build mixed representations of temporary obstacles that coexist seamlessly with the static map data. The map provides not only the coordinates, but the context and the rules of engagement.
The third trend connects this cognitive guide directly back to the vehicle's own sensors. Deep coupling with perception.
Yes, the relationship is shifting from loose coupling, where the map and sensors sort of generally inform each other, to deep synergy. The map now acts as a vital prior knowledge guide.
How so?
For instance, at a complex intersection, the map can reduce the required search range for the vehicle's cameras, boosting the efficiency and reliability of lane line recognition algorithms by giving them a head start. And in return,
The vehicle's perception data is instantaneously fed back to update the map.
you've got it. That's the concept of perception as mapping. This dynamic feedback loop, relying on high-efficiency temporal alignment, is the engine of the continuously self-evolving system.
It's a perpetual knowledge refinement system. Finally, given that maps contain highly sensitive geographical data, how does the strategic roadmap address the necessary security focus?
Security is mandated to be fundamental, not an afterthought. Investment is required in next-generation communication standards like 5G, 6G, and V2X for secure, high-bandwidth data exchange.
But it's more than just the connection, right?
Oh, much more. Critically, the roadmap requires enhanced protection for sensitive geographic information, using techniques like data encryption and digital watermarking to protect intellectual property. The goal is to establish a standardized, auditable security chain spanning the entire data lifecycle,
From collection to distribution.
from crowdsourcing the raw data to processing, storing, and distributing the final map product. This ensures what's called full-link traceability.
The security chain is vital, especially for enabling the rapid update frequency required for L4, L5. Let's look at the quantitative milestones for this map evolution, starting with 2030.
The 2030 goals are focused on foundational deployment and establishing a performance floor.
Okay, what are the numbers?
For update frequency, the goal is significant. Advanced ADS maps must achieve weekly static data updates, with key local dynamic data updated daily. High-precision maps aim for near real-time updates for key elements, subject only to policy allowance.
And coverage.
In terms of coverage, ADS maps must cover all public roads domestically. HD maps must cover all major Tier 1 and Tier 2 cities, the critical, most complex driving environments.
And the security goal is to fix that regulatory friction problem.
Yes. The security goal is establishing comprehensive security control systems and supporting online quick review for incremental map updates, systematically overcoming that bottleneck we noted in the RoadMap 2.0 assessment.
That online quick review is absolutely key to moving from weeks to hours or minutes for an update to be legally approved. Now, moving to the 2035 goals, this is the expansion and real-time security phase. How does the system scale up?
It scales up exponentially in both speed and coverage. Update frequency accelerates again. ADS maps achieve daily static data updates, and for key local data, that becomes hourly.
Hourly updates, wow.
And HD maps now update non-key elements daily. The map is becoming exponentially fresher, moving closer to reflecting reality instantaneously. Coverage hits near saturation. ADS maps must cover all public roads domestically. HD maps achieve full coverage of Tier 1 and Tier 2 cities.
And the security mandate tightens.
It has to. The system must support real-time dynamic audit review of time-space data and achieve full lifecycle security monitoring. The data must be instantly auditable as it flows, meaning the regulator can check its compliance status on the fly.
And finally, the ultimate vision for the 2040 goals: total integration and commercialization. This sounds like the complete realization of the self-evolving system.
By 2040, the industry aims for complete integration and minimal latency. For update frequency, HD maps achieve quasi-real-time updates for all elements, constrained only by national dynamic auditing policies.
So the goal is the functional equivalent of change discovery equals instant legal update.
Precisely. This means the map is no longer historical data. It's a real-time regulatory compliance document. For coverage, high-precision maps must achieve full coverage of all public roads domestically. The technological distinction between ADS maps and HD maps just collapses, as all maps are HD quality.
In security.
Full lifecycle security protection and dynamic supervision must be realized. And critically, the system should enable data flow transaction and platform-based trading.
So a commercial model.
A viable, sustainable commercial model built on secure, tradable data exchange, which justifies the immense infrastructure investment.
That transition from a geometric data supplier to a real-time, secured, dynamic knowledge broker is massive. That completes Pillar 1. Now let's move to Pillar 2, high-precision positioning roadmap. If maps provide the static knowledge of the world, we need an anchor to ground that knowledge in real time. This is the global guarantee.
Positioning is the anchor for every single spatial calculation. Without centimeter-level PNT, and PNT stands for positioning, navigation, and timing, the autonomous system is fundamentally unreliable.
And the landscape here is really defined by the rise of global navigation systems, and the roadmap highlights the critical strategic role of the Beidou Satellite Navigation System, BDS. Beidou achieved global networking recently, didn't it? What is the strategic significance of Beidou being at the center of this roadmap beyond just national pride?
BDS completed global networking in 2020. This positioned the domestic GNSS industry to leverage Beidou as the primary signal source for both ground-based data, terrestrial reference stations, and space-based augmentation services.
And the strategic significance is?
It's all about national autonomy and supply chain security. Relying on foreign GNSS infrastructure, like GPS or GLONASS, for critical national transport and defense systems represents an unacceptable strategic risk. By leading with BDS, the roadmap ensures full control and independence over the time-space data that underpins all L4, L5 systems.
How does that system currently compare to global players like Trimble or U-Blocks?
Well, globally, the industry leaders are very mature, offering robust fee-based commercial services. Domestically, companies like Kiangson Location and China Mobile have rapidly established nationwide enhancement services using techniques like Network RTK and PPP RTK.
And they're already competing globally.
They are. Kiangson's Global Pass service is a great example of this outward expansion, and it relies on the stability of the BDS system.
The rapid commercial adoption is a clear indicator of market maturity, too. Over 3 million mass-produced vehicles using these services by the end of 2024 is a pretty significant metric.
It absolutely is. It demonstrates that the technology is no longer confined to test fleets. It's industrialized, and it's driving L2 and L3 functionality in consumer cars right now.
Let's break down the technical development for positioning into its 3 layers: hardware, algorithms, and services. Starting with hardware, what is the core challenge in achieving full domestic autonomy here?
The primary focus is on achieving autonomy and cost reduction in vehicle-grade components. The combined GNSS systems, modules, and most critically, the core navigation chips.
Where's the gap?
While local companies are competitive in system integration, global leaders like U-Blocks, Trimble, and Qualcomm still dominate in core component autonomy. This is especially true concerning high-end inertial components like MEMS gyroscopes and advanced chip manufacturing processes.
So bridging that gap is essential.
It's essential for supply chain security and meeting the 2040 cost targets.
Now, onto the algorithm layer. It sounds like the engineering goal here is to merge all possible data sources into one single, reliable PNT system.
That's the entire engineering challenge. Synthesizing chaos into centimeter-level truth. The algorithm evolution transitions through 3 complexity stages.
What are they?
First, basic satellite algorithms like RTK and PPP. Then combining GNSS with inertial measurement units, or IMU, using various coupling methods. And the ultimate goal is fusion algorithms.
Fusion, so that means everything.
Everything. This convergence incorporates every available source vision, LiDAR, 5G signal information, ultra-wideband, and maps to achieve seamless centimeter-level accuracy in all complex scenarios.
Whether that's deep inside a tunnel, in an urban canyon, or an underground parking garage.
Exactly, places where satellites can't see.
When we talk about reliability for L4, L5 systems, you mentioned key regulatory acronyms, FUSA and SOTIF. Can you quickly clarify what those safety acronyms stand for and why they are the absolute ceiling for high-level autonomous commercial deployment?
Absolutely. This is crucial for understanding the performance mandate. FUSA stands for functional safety. This covers the potential for failure due to hardware malfunctions or systematic errors within the electronic systems.
So it ensures the system responds safely when something breaks.
Right. SOTIS stands for safety of the intended functionality. This is about ensuring safety in the absence of a failure, but in the presence of external complexity.
Like a weird temporary road sign or an unusual object on the road?
Exactly. The combined PNT system must meet these stringent requirements to guarantee high reliability, continuity, and integrity, especially when signals are weak or obstructed.
That makes the positioning task incredibly difficult. It has to be accurate, continuous, and compliant with the highest safety standards. Finally, the service layer. How do you guarantee reliability at scale globally, regardless of atmospheric conditions or local network quality?
The focus is on star-ground integration. This is developing unified global time-space benchmarks using integrated satellite ground network services. This integration creates a highly resilient network.
How does it do that?
By blending satellite signals with thousands of fixed terrestrial reference stations, the system can correct for signal errors caused by atmospheric conditions and ensure continuity and high reliability, delivering the necessary high availability, which is mandated to be greater than 99.99%.
Now for the positioning roadmap deliverables. Let's look at the 2030 goals, focusing on urban core coverage and autonomy.
By 2030, the focus is on internal self-sufficiency. Service coverage must encompass major domestic cities across full scenarios, so indoor, outdoor, tunnels, with service availability exceeding that 99.99% mark.
And the hardware.
Hardware autonomy is the centerpiece. The goal is to achieve core positioning chips and modules through domestic self-research and secure full-length autonomous control. The resulting hardware has to be integrated into the domain control architecture of the next generation of connected vehicles.
And accuracy.
Accuracy targets centimeter-level precision in key scenarios, including areas with heavy obstruction where GNSS signals are traditionally degraded.
The 2035 goals then aim for a truly national network and full scenario capability, scaling up that reliability.
By 2035, coverage expands dramatically and robustness increases significantly. Service coverage must extend to the entire domestic network across all scenarios, and critically, centimeter-level accuracy must be maintained even in areas without communication or satellite signals.
Relying heavily on those robust fusion algorithms and high-end IMUs.
That's right. Hardware autonomy matures into industrialization. The goal is the realization of mass production and autonomy of multi-source fusion positioning domain controllers, fully meeting those vehicle-grade FUSA-SOTIF requirements nationwide.
And the ultimate target for accuracy is simply everywhere.
Achieving seamless, full-scenario, centimeter-level high-precision positioning across the entire country.
And the final objective, the 2040 goals, seems geared toward competitive global reach and standardization, solidifying Beidou's role on the world stage.
The 2040 goal is explicitly about securing global market share and technological influence. Service coverage must achieve global coverage of real-time, high-precision, high-reliability, and high-security positioning services, with BDS taking the lead role.
Cementing its status as a global competitor.
Right. And hardware autonomy focuses on achieving low cost and high integration of key components, while simultaneously driving the global standardization of high-precision positioning technology, effectively exporting the domestic standard worldwide.
It's clear that maps and positioning lay the spatial and temporal foundation. But as we discussed, single vehicle intelligence hits a wall of cost and fragility.
It does.
That's why the third pillar, smart road infrastructure, is so essential. This is the extended perception system that solves those physical limitations.
This pillar represents the tangible implementation of that vehicle road cloud integration strategy. The rationale is purely operational. Utilize smart infrastructure, radars, cameras, specialized roadside edge computing units to fundamentally solve single vehicle limitations.
Like restricted perception range and decision-making weakness in complex environments.
Exactly. This not only enhances safety, particularly by eliminating blind spots, but it also drives major efficiency goals, like enabling high-speed, coordinated vehicle platooning with aggressive targets like optimizing traffic flow by 20% or more.
A 20% improvement in traffic flow across a national network would be a staggering economic multiplier. The national strategic push sounds very strong here, pushing a leapfrog strategy.
It is a deliberate, aggressive strategy designed to surpass existing global models. Policies are supporting pilot programs that mandate 5G network coverage, rapid deployment of V2X direct communication roadside units, and the simultaneous construction of roadside sensing equipment and edge computing systems.
And the deployment has been fast.
Incredibly rapid. Over 20,000 kilometers of test roads are open, and 7,000 kilometers have already been upgraded to these standards. The focus is on implementing the vehicle road cloud integration standards systematically across major urban and highway networks.
Let's break down the technical architecture for smart roads. The framework uses a three-in-one approach to define the functions of the roadside unit. What are those three integrated functions?
The core technical architecture involves three intertwined functions that have to operate seamlessly. First is traffic perception. This is the acquisition of real-time environmental data.
So monitoring traffic flow, detecting accidents?
Traffic flow density and speed, detecting traffic events like accidents, broken down vehicles, construction, abnormal behavior, and sensing basic environmental conditions like weather and road surface status. The key goal here is all-dimensional road target sensing, achieved through the sophisticated fusion of multiple sensor sources, primarily radar and vision.
The eyes and ears of the road, constantly monitoring traffic and conditions. What about directing that flow?
That's the second function, traffic control and guidance. This involves the dynamic optimization of traffic flow based on the perceived data. Key technologies include adaptive signal control.
So traffic lights that change in real time based on actual congestion, not fixed timings.
Yes, and V2X information distribution, sending immediate localized alerts directly to connected vehicles, and managing things like smart parking and road toll services.
And the most critical layer for achieving L4 safety and those low latency autonomous decisions, roadside computing.
This is the brain at the edge. Roadside computing handles real-time data processing and local decision-making. Through Edge Cloud Synergy, the roadside unit provides low-latency collaborative services. It ingests the raw sensor data and immediately generates a comprehensive, unified environmental model, what's called the God's Eye view.
Which allows for instantaneous collaborative decisions like collision warnings and path planning adjustments.
And that low-latency processing at the edge is the difference between an alert arriving in time to prevent a crash and arriving a second too late.
Now, let's look at the smart road milestones. These KPIs are highly quantitative, focusing heavily on coverage, accuracy, and especially speed. Starting with the 2030 goals, establishing the pilot and performance floor.
By 2030, the foundation has to be robust. For coverage, key city smart intersection coverage must reach 90%.
90%. So nearly every major intersection in large cities is smart.
Yes, and smart highway coverage must reach 20% nationwide, prioritizing critical corridors. For perception accuracy, traffic flow and event recognition accuracy must be very high, hitting 95% or better.
And the computing efficiency, the latency metrics.
This is crucial. Fusion perception target position accuracy must be less than or equal to 50 centimeters. Collaborative decision correctness must be 95% or better. And the critical real-time decision time must be less than or equal to 100 milliseconds.
That 100 milliseconds is already approaching human reaction time. For a system to detect, process, and broadcast a warning in a tenth of a second is fast, but the 2035 goals demand even higher performance scaling up and higher precision.
The requirements tighten dramatically as the system moves from pilot to mass deployment. Coverage. Smart highway coverage increases to 50% nationwide. Perception accuracy improves further to 97% or better.
And the computing efficiency. This is where the major technical leap happens, right?
It is. This is for advanced safety applications like tightly packed platoons. Fusion perception target position accuracy is tightened drastically to 20 centimeters or less.
20 centimeters. To understand that, that's the difference between knowing you are in a lane and knowing the exact position of your tire relative to the painted line in a tight curve, even in heavy fog.
That's a great way to put it. Collaborative decision correctness must approach perfection at 99% or better. And the real-time decision time is halved again, required to be less than or equal to 50 milliseconds.
Shrinking the decision time to 50 milliseconds is a huge technical hurdle at scale. A human driver's average blink takes between 100 and 400 milliseconds. The infrastructure is being designed to operate faster than the blink of an eye.
Exactly. And by 2040, the system must achieve full deployment and optimal speed, pushing the absolute limits of physics and engineering.
What are the ultimate metrics for 2040?
By 2040, the infrastructure becomes the nationwide norm. For coverage, county level and above city smart intersection coverage must be 100%. Smart highway coverage must reach 70% nationwide.
And accuracy.
Perception accuracy is near perfect. Traffic flow and event recognition accuracy must be 99% or better. And for roadside computing efficiency, this is the ultimate target for safety and responsiveness. The real-time decision time is reduced once more to an ultra-low latency of less than or equal to 20 milliseconds.
20 milliseconds. That is the mathematical requirement for true level 4 safety at high speeds. If a vehicle is traveling at 70 miles per hour, 20 milliseconds is the required response time to maintain safety during complex collaborative maneuvers.
It ensures minimal delay in collaborative decision-making between the road and the vehicle, ensuring that the infrastructure-level warning or decision is received and acted upon almost instantaneously. It compensates for the vehicle's own decision latency.
The scale and performance demands across all three pillars, maps, positioning, and roads, are just astonishing. Now that we've established the 2040 vision, we need to address the practical reality. We've seen that the previous roadmap struggled with regulatory friction and scalability.
Yes.
What are the major intertwined obstacles standing in the way of achieving these quantitative benchmarks?
Here's where it gets really interesting. This is not just an engineering challenge, it's a policy and industrial challenge. Achieving these benchmarks requires confronting three intertwined core challenges that span technology, policy, and industry collaboration.
So the blueprint is ambitious.
Incredibly ambitious. But success depends on systematically addressing these structural barriers.
Let's start with challenge one, technical hurdles. Where are the fundamental technological breakthroughs still needed beyond just incremental improvement?
We need major leaps in complexity, cost control, and security systems, and we need them all at the same time.
Okay, break that down.
Regarding complexity and reliability, significant breakthroughs are still needed in multi-sensor fusion algorithms. It's not enough to simply fuse the data from the roadside radar, the vehicle's camera, and the map data. The system has to maintain high reliability and availability, meaning it never fails, especially in adverse weather conditions like heavy snowfall or thick fog, where visual sensors are essentially useless.
And what about cost?
The cost and compute problem. Both the vehicle and the roadside units require massive compute power for real-time, low-latency processing. This high compute power has to be achieved while strictly controlling cost, miniaturization, and power consumption to allow for the economic viability of mass deployment. We're talking about deploying thousands of powerful computers along every major highway in the country.
And given the highly sensitive nature of the geographical and dynamic data being collected, security has to be an absolute foundation.
It is non-negotiable, especially for critical national infrastructure. Establishing full end-to-end data encryption, comprehensive privacy protection, and robust anti-spoofing technology systems is essential. This prevents unauthorized interference with navigation or map data, ensuring the absolute security and integrity of this sensitive geographic information.
That leads directly into challenge two, standards and regulatory friction. We identified this as the primary bottleneck in the last roadmap review. What needs to change in policy and standardization?
Regulatory friction is the strategic accelerator or brake. First, there is the massive, pervasive issue of interoperability. The lack of unified standards and protocols across diverse vendors, different automakers, different road unit manufacturers, different cloud platforms creates costly data islands.
And if they can't talk to each other?
If different vehicle brands and road units cannot seamlessly exchange and interpret data using a common language, the entire vehicle road cloud ecosystem collapses back into isolated systems. It fails to achieve that network-wide coordination.
And the map approval process, which you called the slow, traditional governmental auditing.
That is critical for L4 scaling. The slow, traditional governmental map approval process must be completely revolutionized. It must be replaced by AI-based, online automated review and compliance mechanisms to support the required quasi-real-time map updates we talked about in the 2040 goals.
Because if a critical road change, like a new lane closure, takes weeks to be approved, the HD map instantly becomes a safety hazard.
It no longer reflects reality. This requires immediate focus from a policy perspective.
Beyond maps, what about the overarching legal framework necessary for full commercialization?
Legislation governing autonomous vehicle entry onto public roads, cross-border data flow for globally operating firms, and most urgently, accident liability needs urgent attention and completion. Without a clear legal and regulatory environment defining who is responsible when an L4, L5 system makes a mistake, the industry just cannot achieve the necessary level of large-scale commercial deployment.
Finally, let's discuss Challenge 3, industrial ecosystem barriers. The technology might be ready and the policy might evolve, but industry structure itself can be the biggest hurdle.
This challenge revolves around proprietary data and supply chain independence. First, the data sharing wall. Intellectual property issues, data ownership disputes, and data confirmation problems currently prevent seamless data sharing between automakers, map providers, and infrastructure operators.
Because automakers view the data collected by their fleets as their unique intellectual property.
Exactly. And this data withholding severely hinders the maximization of ecosystem value because the entire crowdsourced, continuous learning closed loop depends entirely on shared data flowing freely and safely.
If the data isn't shared, the system fundamentally cannot self-evolve as envisioned in the 2040 strategy. What about supply chain risk?
Supply chain autonomy is a major focus, directly linked to that Beidou strategy we discussed. The roadmap requires dramatically increasing the domestic rate of core components, high-end sensors, core chips, operating systems, and high-precision inertial components to mitigate global supply chain risks and ensure full control over critical infrastructure technology.
Moving from relying on global providers to achieving self-controlled mass production.
That's the goal.
And the elephant in the room,
Yeah.
the sustainable business model. These infrastructure projects, deploying thousands of roadside computing units and maintaining global positioning networks, are immensely expensive upfront.
They are. And commercial model viability is paramount. The high initial construction costs and the subsequent high operation costs of smart roads and cloud platforms require exploring diverse and sustainable business models. This cannot rely solely on government funding.
So what are the options?
Potential models include government investment balanced by data service fees levied for high-value time-space data access, specialized subscription fees for connectivity services, and platform-based data trading mechanisms, as specifically outlined in the 2040 goals for data flow transactions.
We've covered the aggressive goals for all three pillars, maps, positioning, and roads, and outlined the massive obstacles that must be systematically cleared. It's a comprehensive three-pillar national strategy aimed at achieving global leadership.
That's right. If we step back, the analysis shows a singular focus on setting quantitative high standards. We're talking centimeter-level accuracy, millisecond-level response time, and demanding national coverage by 2040, all while ensuring domestic control of the underlying technology.
So what does this all mean for the future of transportation? When this 2040 vision is realized, how will the system feel fundamentally different for the end user, for you and me?
The resulting transportation system, the new era, will possess three core defining characteristics. First, it will be truly self-evolving. Through that tight, continuous data-closed loop where vehicles contribute data, the edge and cloud instantly process it, and the maps and infrastructure are instantly updated, the entire system is constantly learning and optimizing its performance.
So it guarantees sustained iteration of both safety and efficiency without a human in the loop.
Exactly.
Second, the symbiotic nature.
Symbiotic and win-win. This means the system is designed to benefit all participants. The sophisticated infrastructure facilitates faster, safer traffic flow. The better flow enables more reliable autonomy for vehicles, and that more reliable autonomy generates better, more valuable data for the ecosystem. It's a virtuous feedback cycle.
And finally, the ultimate payoff, the efficient closed loop.
The tight collaboration between intelligent, connected vehicles, smart cities, and the highly reliable time-space data platform will maximize energy efficiency by enabling optimized speed profiles and platoon driving, maximize traffic throughput by dynamically routing traffic in real time, and most importantly, minimize overall societal operating costs, creating massive sustainable societal value.
The most profound transformation isn't just self-driving cars roaming our streets, but the fact that the very road beneath the vehicle is becoming a dynamic, highly regulated data processing nerve center, operating faster than a human can blink.
It is.
This shifts the safety burden, the data collection burden, and the competitive landscape entirely. This means the core knowledge isn't just in the car's processor, but in the environment itself.
It creates a foundational tension for the future of driving. If the infrastructure is providing the centimeter-level positioning, the real-time collision warnings at 20-millisecond latency, and the up-to-the-minute cognitive map, the question shifts from how intelligent is the car's computer to
What happens when the infrastructure starts driving the car?
exactly.
Yeah.
The infrastructure provides the safety, the efficiency, and the context. It becomes the ultimate co-pilot, or perhaps the driver itself.
A fundamental shift in control and intelligence that changes everything we understand about transportation architecture. That is certainly a thought to mull over as we watch this aggressive three-pillar roadmap unfold over the next 2 decades.
Indeed. It forces us to redefine what driving even means when the road is doing most of the perception and optimization for you.
Absolutely fascinating deep dive into the 2040 Intelligent Infrastructure Roadmap. Thank you for guiding us through the milestones, the architectural components, and the inevitable challenges.
My pleasure. It was a great discussion.
To our listeners, stay curious, and we'll catch you on the next deep dive.
Until then.